you. Yeah, let me start by, this is loud, is it okay? Is the microphone okay? Yeah. Good. Let me start by thanking Dr. Mohades and his lab for organizing this event and for hosting. I think part of the reason that this is such a successful event over now 11 years is that it's organized so well, and everyone who visits this feels so welcome that people continue to want to come. I will talk about algorithms for trajectory analysis for this week, and the first lecture will be about similarity. So, and the not so secret agenda for today will be to talk about the Fauché distance. So I know that many of you are already experts on the Fauché distance. So 2 years ago there was also a full week of Fauché distance by one of the speakers, and many of you do this in your research also. So maybe this first lecture you can relax, and then the remaining lectures will cover other things. But I think so Fauché distance is very fundamental for many other analysis tasks that I want to address over the week. So that's why I'll start with that. So the type of data I want to talk about is trajectory data. So trajectory data occurs in many different applications and settings. So here are a few examples. So a trajectory is essentially just a path of a moving object, and you might have data about hurricanes and you want to know where the hurricane hits. You might have data about vessels, and there mostly the applications are in surveillance. Sports data to analyze the performance in sports, and the type of data which I in particular like is animal data, which is used in ecology a lot to understand the behavior of animals, how migration, for instance, works, and so on. So trajectory data is about moving objects. So in principle, a trajectory is just a mapping of time into Euclidean space. For us, typically 2 or 3 dimensions. Most often we think of this in terms of 2 dimensions because in many types of data, the 3rd dimension, so height, is not so reliable. So we're essentially talking about 2-dimensional curves parameterized over time. So the path of a trajectory is really just a curve. But now if we think about the data, then data is somehow collected. So here with these devices, for instance, and then because of limited battery, this device might only collect data every once in a while. So depending on kind of the size of the device and whether it can be recharged, it can be anything between fixes every minute, but also just every few hours. In this example, for instance, you can only get data when the turtle actually resurfaces. So your data set might look like this, and then there are large stretches, so several days, where you don't actually get a data, and then you get a data point. So the data is not really this nice continuous trajectory that we would like to have, but it's essentially a sequence of data points. So this would be a sequence where I have the spatial coordinates, and let's think of it in 2D, then have 2 spatial coordinates and a timestamp. And then very often we will think of this as a polygonal curve. So we'll just we have a measurement here and a measurement here, and we'll simply assume that the object moved in with constant velocity between those 2 data points. So that is not necessarily a very realistic assumption, but it gives us a nice geometric object which we can now use in our algorithms. So what type of questions do we want to address in trajectory analysis? So typical questions could be, so let's have here's another data set of a bird which is flying along this coast, but then also over here. So typical questions could be, okay, are 2 trajectories similar or not? So if I have 2 specific trajectories going from here to down there, I might ask, are they similar? I might want to detect typical routes. So here, for instance, you see kind of this big cluster which is used very often. so I might want to be able to detect that. If I have several data sets, so I'm tracking several animals, then I might want to know properties of the animals in terms of how they interact. So for instance, whether they move in a group. So more and more data is generated where actually several animals are tagged, so get a GPS tag, and then you can ask questions about how these animals interact. In a non-animal setting, mode of transportation is a very common question. So was this person using a bus, a car, a bicycle, or going by foot? And a very common question is also where does movement change? So I have a long track of some kind of object, and I want to know, I want to cut it into meaningful pieces, which means I want to know where did the movement change, which is closely related to for instance, this question of mode of transportation. So this is more kind of on the, if we think about a specific data set, in terms of fundamental algorithmic questions, one way to group them is in terms of on how many trajectories we are performing this analysis. So if I'm just looking at one trajectory, very often, which is less an analysis question, but more a question of bringing the data into a format which we can work with, is some kind of pre-processing, which might be cleaning, which is less interesting from the geometric perspective, but simplification, so getting a compact representation of your trajectories. Another question is segmentation, so you have a huge trajectory and you want to cut it into small pieces where every piece is somewhat meaningful, and this question of finding recurring patterns, so finding things that happen maybe regularly or simply happen often, like you have one trajectory that chooses the same road many times. On two trajectories, the most common question is similarity. You can ask similarity in terms of the whole trajectories, but you can also ask similarity in terms of small parts of the trajectories. So maybe not everything is similar, but there may be a part of the trajectories that are similar. And then there's a big group of questions on, if you have many trajectories, you might want to perform clustering. You might want to learn something about how these trajectories group. If you have many trajectories, which is actually also related to the clustering, you might want to find one trajectory which represents your data set well. And there's a kind of maybe on the more applied side, the question of, if you have a huge set of trajectories, how to actually visualize them. So what I'm going to talk about today is a similarity computation. And the reason I'm doing this first is that it relates to nearly all of the other questions. So if you think about simplification, for instance, so you want to, given a trajectory, have a kind of compact way of representing that trajectory with fewer data points, then essentially you're asking about, I have a trajectory, I want to have a similar trajectory with fewer vertices, so it's about similarity. Also clustering is about grouping similar trajectories, so obviously before you can do clustering, you have to talk about similarity. So when we do similarity on trajectories, so in principle trajectories are not just spatial, but they're space and time are important. But very often the spatial similarity is more important. So it's less important whether they happen at the same time, but more important that they use the same path. So this is an example where, so here this is from a query setting where you can, so there's a yellow arrow here which is a query, and then in the setting all similar sub-trajectories were reported within, so this is football data. There it's not so important how fast this movement was. I mean, maybe it is, but often it is not. But just that it's spatially similar. And you can also think of settings where if you look at data on roads, for instance, then obviously the time very much depends on traffic. But still, you might want to, if you are just interested in finding frequent routes, then you ignore whether there was a traffic jam at one morning or you came through quickly on another one. So we will focus on spatial similarity. So in the GIS literature, there are many similarity measures. So many of these papers start with, okay, we have this application, we want to perform some specific similarity task. We briefly argue why other measures are not suitable. We come up with our own measure, and so on. So there are lots and lots of papers, but I would argue that essentially many of this boils down to a few very fundamental measures, which I now want to focus on. So one maybe very simple, and I would argue too simplistic approach, is simply to take your trajectory, map it into a high-dimensional space, and then perform similarity in this high-dimensional space. So that is actually used still quite frequently. So I have this trajectory. It has 5 data points. It is in 2D. So I can just map it immediately to 2 times 5, so into a 10-dimensional space. I get a point. And now, if I have several such trajectories, I can take the Euclidean distance in this high-dimensional space. And then I can do my favorite techniques for high-dimensional data. The problem here is that it's very difficult to say, based on what happens in 10 dimensions, whether these were actually similar. So for instance, if I look at these two trajectories, so they only differ by having, this one has this data point very early, this one has this very late, but in terms of the geometry, in particular, if you would place them even closer to each other, they're essentially the same. But if you do this mapping, so they have 3 points, you're in 6 dimensions, then these data points will be the trajectories will look very different because these 2 points are very different. And then you also run into the issue if the trajectories have different number of data points, then there's not even kind of one space that you might want to map to. So here they would look non-similar, and I would argue that the trajectories as such are similar. So if we look at general geometric methods for comparing shapes, then I think the first one that comes to mind is Hausdorff distance. So Hausdorff distance, just to remind you, so we have 2 geometric shapes as input. In our case, it's polygonal curves. And now the Hausdorff distance, so the directed Hausdorff distance from P to Q is for any point on P, I look for the closest point on Q. So for this one, that would be here, for instance. And then I take the maximum of this, so that would be this distance here, that is the directed Hausdorff distance from P to Q. Then I take the directed distance from Q to P. Again, I look at the maximum, I take the maximum of those 2 maximums, and that is then the Hausdorff distance. So that is a very important measure for general geometric shapes. Again, I would argue it's not ideal for trajectories. And one example would be the following. So this is maybe one trajectory, so it goes around once. This is another one, it goes around twice. So let's say, assume they're spatially actually very close. Then the Hausdorff distance, in particular, if you draw these even closer together and even closer to P, the Hausdorff distance will be very small. But the curves or trajectories, they are quite different, because this one actually does 2 loops, this only does 1 loop. Might even be that Q does a loop in the other way around. And still, from the Hausdorff distance perspective, they would look very similar. So measures that work better here are measures that try to align these curves. And so let's first look at measures that align sequences. So if we think of, so we have these 2 polygonal curves, but we can also simply think of them as a sequence of their vertices. And that is done very often. And then the most used measure, I would say, in many application fields is dynamic time warping. For trajectories, also longest common subsequence is used quite frequently. And I would like to have a brief look at those. So the idea of dynamic time warping, so imagine this is your time axis here. So essentially your spatial coordinate is just on this axis. Then if you take those 2 curves, then if you would simply align point by point, then you would get this alignment. But if you think of them kind of laid over each other, then you might want to actually align this feature with that feature. And dynamic time warping allows this because it gives you a non-linear alignment. So then you map points on this curve to points on that, and vice versa. But you do so in a way that you allow yourself to essentially map one point to many points here, and in that way, in terms of trajectories, you can think of it that you warp time. So let me briefly talk about how to calculate the dynamic time warping distance. So if these are two curves or trajectories, so what we would want to compute, and again think of them, I mean they're overlaid, so what you would here probably want to do, if you look at this area here, you would want to map this downward going slope, this blue downward going slope with this red downward going slope. And with dynamic time warping, that would mean that here, essentially, while this is going down, you're mapping it with a downward going path of the blue. Which then here, for instance, means that on the red one, you'll have to wait for a while. And a different perspective on this is if we look at the distance matrix. So here we have a column for every vertex on the C here. We have a row for every vertex on Q. This is the distance matrix, so for any 2 points, I just look at the distance. And now such an alignment is essentially a path through this distance matrix, which starts at the lower left, goes to the upper right, and the steps are always either horizontal, vertical, or diagonal. And then we want to define what is the quality of such a path, and for dynamic time warping, if I here take distances, and more generally I have some weights, then I'm going to take the sum of weights, so in our case the sum of distances along the path. I'd like to briefly talk about how such a path is computed, and for that I would like to just very briefly go a step back, and I'm not sure whether everyone knows dynamic programming. I'm not sure. Do you think it's a good to explain it briefly? Huh?
Everyone knows.
Everyone knows. Okay. Then I will skip these slides. That's fantastic. I can skip these slides. So then in terms of dynamic programming, we only need the recurrence, and the recurrence for dynamic time warping is simply, so we're looking at what for any cell we want to know what is the best path up to that cell, including the cell, and then the corresponding recurrence is the distance of the two curves at that cell plus the minimum of either doing a horizontal step to that cell, a diagonal step, or a vertical step. And with this recurrence, simply by using a quadratic size table, I can easily compute this distance in quadratic time. And that is essentially also optimal, so you can prove that as long as some complexity theoretical assumption holds, which is a strong exponential time hypothesis, that you cannot do it much faster. In terms of trajectories, let me briefly talk about time a little bit more. So if we want to incorporate temporal similarity, so to some extent dynamic time warping does that anyway, because diagonal steps, you can imagine a diagonal step is somewhat cheaper than doing first horizontal steps and then vertical steps. But if we want to incorporate it even more, what we can do is that we limit the warping in terms of how far away it goes from the diagonal. So you can think of the diagonal of being, meaning that every time with every temporal step, you again align the same data points. So if you, for instance, say you should stay within a band or some kind of other shape around the diagonal, then you can enforce temporal similarity if you want to. Okay, so so much about dynamic time warping, and longest common subsequence is very similar. So this often works well, and this is used in applications a lot, but it has one drawback, and that is these measures are non-metric. So we do not have the triangle inequality, which in turn is problematic if, for instance, we want to do clustering. I mean, you can still do clustering, but it is much more difficult. So the triangle inequality is something that's always good to have. And a measure that has this is the Fauché distance. And I know many of you know of the Fauché distance. Maybe can I have a show of hands just to get an impression? So who knows the Fauché distance? So it's half, maybe a bit more. Good. Okay, so that half can maybe, I don't know, enjoy the slides, think about open problems, or whatever. So this is the Fauché distance, first intuitively, and then I will also give the formal definition. So we have these two curves or trajectories. So for us, from now on, I mean, we mostly see the trajectories simply as curves because they are curves parameterized over time. So we have these two curves, and now again we want to align them, but now we are thinking of continuous curves. And the way to illustrate the Fauché distance is we have this man and we have this dog, and they have a leash between them. So the man has a dog on the leash, and they both need to walk along their respective curves, but they are allowed to change their speed. So they're not allowed to go backwards, but they're allowed to change their speed. So the man is allowed to go faster than the dog, or dog can go faster than the man. So here, for instance, if you assume they want to stay as close as possible, if they both continue walking, you will need a very long leash. So here it's maybe better for the man to first walk and then for the dog to walk, because then you don't get this distance here, so you don't need this leash, but you only need a leash of this length. So the Fauché distance can be expressed as if you have this traversal, so man on one curve, dog on the other one, they may vary their speed, not go back, but not go backwards. The Fauché distance is essentially the minimal leash length needed for such a traversal of the curves. As a definition, so if we have two polygonal curves, then we can see the Fauché distance as, so essentially here the infimum is over all possible ways of walking, which is reparameterizations of the two curves. So we have these reparameterizations, which in this setting of curves you can simply see as continuous non-decreasing functions. So we take the infimum over all of these, and then for each of those we look at the maximum between the two resulting now reparameterized curves. So for the pair that I showed to you, the maximum distance occurred here, and now I look at all ways how man and dog could go, and I take the one that gives me the shortest leash length. Another way to look, so this is the continuous, or the Fauché distance simply, sometimes called continuous Fauché distance, because there is a discrete version also. So let me briefly talk about the discrete version, because it is used quite frequently. So here, instead of, so let me show those curves once more. Instead of looking at the continuous curves, I again, like in dynamic time warping, only look at the vertices, and I only try to align vertices. But now not with a sum as in dynamic time warping, but with a maximum. Which means in terms of man and dog, you can think of two frogs. They're hopping from stone to stone, and you only measure you're not measuring the distance while they're hopping, but only on the stones. It's very similar to dynamic time warping, just that you get a slightly different recurrence. So here you get the maximum of where you want to go to, and then take the minimum over whether you came horizontally, vertically, or diagonally. Yeah, so you're looking for the path where along that path the maximum is minimized. So in an example, so these could be two curves, and now this could be an alignment. So our frogs start here, they both jump here, then one jumps here, they jump here, and so on. And then the discrete Fauché distance in this example probably would be this distance here. So one shortcoming of the discrete Fauché distance that you run into issues if the sampling rate of your trajectories are different, then for instance this point here has difficulties to get mapped somewhere. So I mean you could map it here, but that is large, but also mapping it here is very large, because actually you would like to map it to something here. So let me summarize what I've shown you so far. So we've seen dynamic time warping, discrete Fauché distance, and started to talk about the Fauché distance. If this is an example of two curves or trajectories, so I have here, this one goes from A1 to A2 to A3, B1 to B2, and so on. Then dynamic time warping would try to minimize the sum of distances, or sum of squared distances. So you would here align A1 and B1, A1 and B2, then do the jump to A2 and B3 and to the end. The discrete Fauché distance will try to minimize the maximum. So this distance here from A2 to B3 is fairly large. So in the discrete Fauché distance setting, the alignment would avoid that and essentially align A1 and A2 to B1 and B2 to B4 to A3. So that is, you avoid this large distance, so these distances are smaller, these distances are smaller. But in contrast to dynamic time warping, you see you're somewhat less on the diagonal, so you have more cells, so that's why in dynamic time warping this path would be too expensive. The Fauché distance would align these curves, so it would align A1 and B1, then it would align everything up to A2 still more or less with B1, and then you would slide on both trajectories to the right and kind of nice and continuously end up at A3 and B4. So and this is what we would like to have, and it is, so here's a pictorial representation of how it is computed, but this I want to kind of now in the largest part of the remaining presentation focus on what this diagram is and how we compute the Fauché distance using this diagram. So the Fauché distance most commonly is computed by first solving the decision problem. So instead of asking, given two curves, what is their Fauché distance, we ask, given two curves, is their Fauché distance smaller or equal to some value? And the value here is R, I call R. And if we have such a decision procedure, we can then use it with some kind of, you could say, binary search to actually compute the Fauché distance. Now we want to solve this decision problem, and the way we can look at this is we start with small curves and then extend what we learned there to larger curves. So the two simplest curves would be simply two line segments. So now my polygonal curve here is just a line segment, the other one is this line segment. Now what we look at is essentially the product space of the parameter spaces. So think of the parameter space, this being essentially the parameter space of Q, this being the parameter space of P, and every pair of points on P and Q now corresponds to a point in this product space. So P, so if I look at P is this on this, and it is on this axis, then this point corresponds to this height here. This point on Q will correspond essentially to this vertical line, and this pair P and Q is in this point in the product of parameter spaces. And now if we want to know whether the distance at this point is smaller or equal to R, we can easily check that, and kind of from a more geometric perspective, what we're interested in is if I now draw a disk of radius R around, let's say, this point here, is this other point within that disk. And this allows us to, so what we now want to do is essentially first determine all points in the product space where the distance is smaller or equal to R, and we will then use that to compute an alignment. So the way we could do this is to look at, for instance, I look at the first point on Q, so that corresponds to this vertical part here. And now I can look at everything of P that is within the disk of radius R, so that is this part up to here. So that would be everything up to here has distance smaller equal r. Okay, and let me just do that for a couple of points here. So this is essentially the point on Q where if I move further, then the first point of P is no longer in this disk. So this is the first point where essentially the first point of P leaves the disk. And okay, I will do this for a couple of more points. This is the point on Q where if I slide further, or from this point on, the last point of P is inside. So that's why I get this segment which goes up to the last point, and so on. So what this gives me overall is some region where any point in this region, which corresponds to a pair of points here, has distance smaller equal r. And we call this a free space of P and Q. Now, if we have this free space, I still have to think about, okay, what does it mean to have reparameterizations of P and Q that realize a Fouché distance smaller equal r? So if you think of this discrete setting of dynamic time warping and discrete Fouché distance, what we were looking for was a path in this distance matrix. What we're now looking for, so this reparameterization corresponds to essentially a curve in this space, because it is an alignment of points of P and Q, and as such an alignment aligns always 2 points. We want to match the first point of P with the first point of Q and the last point of P with the last point of Q. So in the R setting, if I just have P and Q as line segments, it means my curve has to start here and end up there. And now the reparameterization will be some kind of continuous curve from down here to up there. But it has to lie completely in the free space. So this curve, for instance, that would be not valid because here I'm going outside of the free space. So if you think of man and dog, whatever they did here, at this point actually man and dog are too far away to use a leash of length r. So this would be valid in that regard because I'm staying in the free space. Should be continuous, and also if you now look at this one, so it stays within the free space and it is continuous. But the problem is that here it goes up and then down again, and in terms of, if you think of it in terms of man and dog, it means that here, so if this is my man, maybe here he's going forward and then he starts going backward, and we said, okay, we shouldn't go backwards, or in terms of the formal definition, it should be non-decreasing. So this is again not valid, but this would be a valid path. So we needed this path to be monotone both in x direction and in y direction. And okay, this already characterizes Fouché distance. So the Fouché distance is at most r if and only if we can find a path with these properties. So it should be continuous, monotone in x and y, and stay within the free space. So this was now for line segments P and Q. So now let's first look at the case where one of them is not a line segment. So P is still a line segment, Q is not a line segment. Then what we did on the previous slide, so here if I look at just this line segment and P, then I would get one such cell. So now Q has several line segments. So it means I get several, for each segment of Q, I get one such cell as we just looked at on the previous slides. And to illustrate why we get these cells, so here at the beginning, so if I start on Q here, this part of P is within the radius r. So that's why here there's free space at the beginning. If I now move, actually more of P will be in this disk. Yeah, so while I was moving here, more of it was in here, and that meant that the free space got larger. But eventually, if I move along the next line segment, so here the disk only touches P. So that means here actually the free space ends, and so on. So here I again touch P, only touch P, and so on. So this is the free space diagram for a segment and a polygonal curve. And we can now generalize that even further to two polygonal curves of longer length. So if P now also is a polygonal curve, then we have, so when P was a segment we got one row. Now P has several segments, then I get several rows, and each of these cells now corresponds to a pair of edges. And what I'm now interested in is there a path from Q1, that is Q1 P1 to QM PM, so to these 2 points, which stays within the free space, which is continuous, and which is monotone in x and y. So here, for instance, this would be such a path. And let me illustrate that. So we start here. Now we move on both curves. So this is man and dog. Now we move on both, but we move more slowly on P. Here we nearly only move on Q, which means that this point will more or less stay where it is. For the next one also, there's just a slight movement on P. Now we move on both. And in the path that I selected here, we first move on P and then move on Q and then move on P again. But such a path is also non-unique. So here we could have also used a path that kind of moved on P and Q simultaneously, as long as we stay within the free space. So for the algorithm then we need to first compute this free space diagram, and that is actually easier than it maybe looks like, because these free space cells, they're essentially so the free space is essentially always an ellipse, which means in particular it's a convex shape. And now if I'm interested in whether there is a path or not, so imagine I have a path that goes through the cells, or continuous monotone, then it is actually not this part up here, for instance. How this exactly looks like is not important for us, because if there's a path through here, then as soon as I enter the cell and I know where I leave it, I just can use a straight line segment. And that comes from the fact that this ellipse here is convex. So what that means is that we need this, what I call critical points along the boundary, so where the ellipse intersects the boundary of the cell. And as soon as we have that, we can forget everything else that happens in the cell. So we really just need to know these points, and then that allows us to determine whether there's a path with the properties that we want to have through the cell. And these points we can easily compute, because what is this point? This point is, I'm looking at the first point of Q, so I'm here, and I want to know how much of P does it intersect. Yeah, so this point, for instance, simply corresponds to this point on P. Then this point corresponds to that point on P, and so essentially just four calculations that I need to do to find those 4 points. So I can do that in constant time, and that means that I can compute the free space diagram in quadratic time. So if my curves have complexity m and n, I can do that in order m times n time. Now in the next step, given the free space, we need to determine whether there is a monotone path from down here to up there. And what we do for that, it is essentially the same as what we did for dynamic time warping and discrete Vichy distance. It is a dynamic program, just that the information that we now need to maintain is a bit different. So if you think of dynamic programming or discrete Vichy distance, when we were looking at a point, we were looking at, okay, what were the best ways of getting there? And here the perspective is, if I look at some edge, let's say here, I want to know whether it is, so this is the decision version, so I want to know whether it is reachable or not. So essentially what I want to propagate is the parts of the free space that are reachable from this point down here. And for that it is actually enough to determine the earliest reachable point on any boundary. So let me show this by an example. So let's say this is a cell that I'm looking at, and I'm interested in paths that enter from down here and leave through this horizontal edge. Then the information that I need is that this point is reachable, if this was reachable. And if I know that this point is reachable, then everything, all of the remaining free part here is also reachable. So it's really enough to determine the earliest reachable point. So in this setting, but that's not always the lowest point. So here, for instance, if I come from a horizontal edge to a horizontal edge, then because here already I have to go this far up, then in terms of what is reachable here, then everything below this lowest point is reachable, but the lowest point now sits here. But if I know, so in terms of the dynamic program, if I know what is reachable here and here, it's easy to determine. So in particular, if I know the lowest point here and whether this here is reachable, I can easily determine the lowest point on this boundary of this free space. So this is an example where the left is reachable, but actually the right is not reachable. So on the right hand side you do not have anything that is reachable because the free space here is too low from this point, seen from this point. But with this we know what we want to propagate, so we can simply, starting here, we find this is the earliest point on that edge reachable, this is the earliest point on that edge reachable, and we propagate this information through the diagram. So on this edge, this is the earliest reachable earliest point that you can reach from the left and also from below. This will give me this point here and that point here. Then more interesting, let me show you for instance this point here. So here the boundary is slightly lower, but because here you have to go up this far, the earliest reachable point is up there. And then you just propagate that through the diagram, and then you know that the Fouché distance is smaller or equal to r if and only if you determine that this point is reachable.
So it's somehow you then don't need to somehow first compute the marginal point of this free space, the upper marginal point of the free space, right? I mean, they're not necessary because we're going to find the lowest possible monotone curve. So many of the upper points of the free space is unnecessary to be computed, right?
Yeah. So the reason you need this upper point is, I mean, indeed, you want to know the lowest point. So you can have a setting. So you can have a setting like this. So this is not free, and this is not free. Then, okay, let me first draw the setting that you are talking about. So if this is not free and this is not free, if I come from here, this was the lowest point maybe here, and now in the next step I know I have to go up here. But I also need the upper point, because here, for instance, I come from here. I want to know the lowest point reachable. But for this I need to know that this point is already in, that the reachable part is below here, because then I know that this is blocked. Yeah, so for that I also need to have the upper boundary. So does that answer your question?
Yeah, but I mean, somehow you can somehow merge the first and the second part of the computation. I mean, don't compute the free space first and then start to look to the.
I do everything at the same time. Yes, of course. Yes, you can do. Yes, of course. Yes, and from a kind of a, let's say, more practical perspective, that is often also a good idea to do, because if, for instance, do you have an example here? I mean, obviously, starting from here, none of this is reachable. So, if you compute your cells while you're going, then if you use your data structure suitably, you will never have to touch these cells. So you will get a faster algorithm. Yeah, so that is possible, certainly, yes. Yes?
The complexity of the XY monotone path is linear, but the complexity of the grid is squared.
Yes.
So by this kind of approach, do we need to compute the whole configuration space?
So there will be, yeah, so I mean there will be inputs
Like that?
actually in many practical applications if the curves are well aligned.
Yeah.
Then your free space will look like you have a white area here and probably not much outside of there.
Is there any study like probabilistic or I don't know, average case? Or
I mean, so I mean, maybe first to kind of without the average case, I mean, you can ask the question, can you do this faster in general? And there, I will talk about that at the end briefly. There are lower bounds saying, okay, in the worst case, you will need the quadratic time. Does that already answer your question? I mean, of course, maybe there are kind of interesting probabilistic arguments or settings that you can look at where you can nicely argue that you need less, and that would be very interesting. Okay, now we computed on a monotone path. So that means we can solve this decision problem in quadratic time, because both of this takes quadratic time. Now, if we want to actually solve the computation problem, we will want to invoke this decision algorithm with suitable values for R. And you can think of this, I mean, so this will not be the algorithm, but maybe a good way to think of this free space is think of the setting where you start with R being 0, so that everything is non-free. And while you increase R, suddenly kind of new paths will occur. But these paths will only occur at specific points in time. And those will be points in time where the combinatorics of the free space change. So let me first say a simple, kind of what is often used in practice, a simple approach to finding the right R is doing just a binary search on the bits. So then you will get order m times n log some kind of accuracy. But that is obviously not a, let's say, theoretically satisfying result. So what we now want to make use of is this, that if you increase R, that there are only some interesting values at which are actually possible to be the actual value where the Fréchet distance is attained, because only at those values new paths occur. So we want to find the minimum R where there is a path, and this minimum R can only occur at a certain number of critical events. So, and there are three types. The first is very easy. It's just obviously the first 2 points are aligned and the last 2 points are aligned. So a possible value for the Fréchet distance is the first point, the first value of R where these can be aligned. So where the first 2 can be aligned and the last 2 can be aligned. The second case is, if you look at now this boundary, now this is R, and right now there will not be a path that goes through the cell, because here it ends. But if you increase R slightly, then as soon as this free space touches this boundary, there might, I mean, if there's a path going here, it can exit there again. So this could be a possible value where the Fréchet distance is attained. And this is determined, so this edge, it corresponds to an edge of 1 point, no, so this, in terms of the, vertically speaking, this is, here I have 1 point on P, and 1 edge of Q. So, and this is exactly a setting where this distance, where R is exactly the distance between this edge and this corresponding point. And because I'm looking at edges of one curve and points on the other one, the number of such events is order m times n. So when did I start? Just to make sure that my timing is right.
We have like 10-15 minutes.
10-15 minutes, okay, perfect. So I have a quadratic number of these events. where essentially where the distance between this edge and that point, so the edge corresponding to this and this point, is R. So that R is an R that we want to check. There's another setting which corresponds to this, also to this discussion here, and that is, I might, for instance, so the same argument would be for vertical paths, but in this horizontal setting, so if I come from here, I will be blocked over here, but if so this, right now I don't have a path, but if I increase R slightly, then suddenly there's a pathway opening here. And since there's a pathway opening here, now there's kind of a new chance for a path going from the lower left to the upper right. So this will be a value of R that I want to check where such a pathway opens. So this corresponds to, I have one vertex on one curve and another vertex on that curve, an edge on the other curve, and these two vertices have the same distance to this edge. So I'm looking at two vertices and one edge, and I get a cubic number of these possibilities. So two vertices, if this is, let's say this has complexity m, then I get m squared times n, and since I do the same vertically, I get also m times n squared. So I have a cubic number of possible events, and now I could do a binary search on these, which would give me running time, let's say, of m squared n plus m n squared log mn. So I first compute all of these events and then do a binary search. So I essentially get a near cubic running time and can solve the problem. With doing this binary search more cleverly, or actually using a parametric search, which you can think of performing this binary search for several different values in parallel, will actually give you a quadratic running time, or near quadratic running time, mn log mn. Okay, so what we have so far is, I talked about various similarity measures, which the best one might depend on the application, but the Fauché distance is one that is very useful, in particular because of two properties. It is metric, and it actually takes the continuous curves into account and not only the data points. And I showed you this algorithm that runs in order mn log mn time. Let me give you some more results on the complexity of computing the Fauché distance. So the algorithm that I showed you was this algorithm, this classical algorithm by Alt and Godau. And so Helmut Alt was also visiting very recently. So you know him if you attended a previous school. We at some point, so we for a long time tried to improve this running time. And we made this drastic improvement of nearly half a log factor. So we improved from n squared log n to n squared square root of log n and some log factors. Essentially the idea being to, instead of doing it cell by cell, is to group cells and then do several cells at once. This is of course not a very impressive improvement. And the reason we eventually we found out why we weren't able to do it better, because Karl Bringmann showed that as long as unless a strong exponential time hypothesis fails, and I'll say slightly more about this very soon, there is no strongly subquadratic time algorithm. So we can still shave off maybe some log factors, but we cannot be drastically faster. So then we also stopped trying to improve it. So more recently, so this shows that you cannot compute the Fauché distance in much less than quadratic time. We recently showed that this is also true if you want to do a 3 approximation. So you cannot get a 3 approximation faster than quadratic time unless a strong exponential time hypothesis fails. And this just shows the free space, a small part of the free space of the gadgets that we use to prove that. So it's this I'd say this construction by Karl is a very clear and nice, also intuitive construction, which I think is worth looking at. Our paper here is it's this huge construction which is very difficult to figure out what's happening, but it all works. Now, let me say just a little bit about some aspects going beyond simply computation. So there are approximation algorithms, but only very little approximation algorithms. So there is this algorithm by Brinkmann and Mulzer, which essentially runs in, if you want to have an alpha approximation, it runs in n squared divided by alpha time. So if you think of possible values for alpha, this is not, this is very far, let's say, at least from the 3 approximation lower bound, because, okay, for any constant, this is not interesting. If you plug in, let's say, square root of n here, so you can get a square root of n approximation which runs in n to the 1.5 time. And the kind of most important idea in the proof is that you look at these vertices and you, and this is actually, I should have said this is for the discrete Fouché distance, not for the continuous one. You group the vertices, that are close to each other, and then while doing the computation in your diagram, making use of that essentially everything that is, so you have this grid overlay the grid with the points, and you make use of the fact that everything within a grid cell you can more or less see as a same point, and then depending on what grid you choose, so you choose that depending on alpha, and then the algorithm that you get runs in this n squared divided by alpha time. There is a 1 plus epsilon approximation, but that only works for specific types of curves, so-called CPEC curves. So the CPEC curve is a curve that if you look at a disk, at any disk, and look at how much of the curve, so how much in terms of length in the disk of the curve is within the disk, then this length within the disk should be bounded by this parameter c times the radius of the disk. So that means if you have curves that do not go through the same area too often, you can actually get a 1 plus epsilon approximation. And that is a result by Driemel, Harpellet, and Wenck. Yes?
We get into this alpha approximation last year.
Huh?
We published a paper with Similarity,
Mm-hmm.
and we get a better approximation ratio for that.
Yes.
N log n plus n to the 2 over alpha to the 2.
Yes. You're right. I forgot. I should include that here. Yes, thank you. Yeah, yes, that is missing here actually. In terms of lower bounds, the lower bounds that we have are all in terms of the strong exponential time hypothesis. So that is a statement that you cannot solve k-sat in less than O to the 2 to the 1 minus epsilon n time for any epsilon. So that's the strong exponential time hypothesis. Typically an intermediate problem is used. This is orthogonal vector problem. So you have 2 sets of 0, 1 vectors, and the question is there a vector in one set and in the other set, which if you take those 2 vectors, they are orthogonal. Essentially, if the strong exponential time hypothesis holds, then no, if there would be a subquadratic time algorithm for the orthogonal vector problem, then the strong exponential time hypothesis would fail. So for the Fouché distance, this is a statement here. For the Fouché distance, the common reduction is to say, I want to show that the Fouché distance cannot be solved faster than n to the 2 minus epsilon time, and the reduction is then to the orthogonal vector problem. So the original reduction that Karl Brinkmann did was directly to the strong exponential time hypothesis, but also his reduction you can see as a reduction to the orthogonal vector problem. And how much time do I still have?
You still have 5.
Okay, 5 minutes. Yeah, I just want to show you the idea of Karl's reduction. So what we want to have is, we have two sequences of vectors, and we want to construct two curves, P1 and P2, such that their distance is smaller or equal to 1, if and only if there is an orthogonal pair of vectors in these sequences. And this will be a very high level idea. So what happens here in his reduction is essentially that you encode the vectors. So given one such vector, you will encode its coordinates in a curve that kind of goes, so for one of the sequences you will encode it in a curve that goes back and forth here all the time, where depending on whether it's 0 or 1, so 0 will be slightly below and 1 is slightly higher, and then the next coordinate is here, 0, 1. And then you do it for all the coordinates. And for the second curve you have something fairly similar, where again you encode 0 or 1 here by 2 points, where, so because his reduction was from directly to k sub t here, you should think of t as being 0, f as meaning 1. So the 0 is slightly further up than the 1. And then the basic idea of this reduction is, if there is an orthogonal pair, then there is a traversal of these curves where on this blue curve I first move around until I come to the point which corresponds to the corresponding vector which will be orthogonal to some vector on the other curve. Then I do the same on this other curve, where I go to move myself to the corresponding vector here. Then I'm able to traverse both of them at the same time, if and only if they are orthogonal. Because if they are non-orthogonal, if they are orthogonal, it will mean that either this one is a 0, and then both of these are close enough, so these have distance at most 1 to this point, or this one is 0, and then both of these are close enough. But if both of them are 1, so this one is here and this one is down there, then the distance, they cannot be traversed at the same time. So that's just in very general terms the idea of this reduction. And as I said, the original reduction here is directly from the strong exponential time hypothesis, but you can think also this, I mean, I now explained it in terms of orthogonal vectors, and you can think of it in terms of orthogonal vectors.
But isn't it the case that such a graph, such a curve, are bad in terms of the definition? You already mentioned that the balls,
Exactly. Here, my next point, yes? Yes. Yeah, so these are very much non-packed. In terms of C-packed, the C would be linear. So in his paper, there's also a reduction that works on C-packed curves. And the idea is in two steps. One, you slightly, so essentially you make several copies of this and place them next to each other, but then to check all pairs you have to, so you partition your sequences into blocks, and then you have to check every pair of blocks, you could say. So, and for that you'll have to place this reduction again and again. That is the basic idea, and then he maps that construction to 5-dimensional space, making use of the fact that in 4-dimensional space there are many pairs of points which just have distance 1. And then he gets a similar results for CPAC curves where you can show that you cannot do better, and it's then close to the lower bound, to the upper bound with 1 plus epsilon approximation. You cannot improve the approximation algorithms, at least if you think of curves in 5D. I'd also like to briefly mention a few variants of the Fauché distance. So we've seen the normal Fauché distance, discrete Fauché distance. Weak Fauché distance is if you think of man and dog, now man and dog are also allowed to go backwards. So it's a bit weaker. That's why it's called weak Fauché distance. It's somewhat more between, you could say, Hausdorff and Fauché distance. And I think it's also a very nice distance measure to study. There's a concept of shortcuts where you can kind of do jumps in the free space. And more recently, there's this concept of K-Fauché distance, which is a generalization of the weak Fauché distance, but you allow yourself to partition the curve into K parts, and then want to have weak Fauché distance between each of these, between always two of these parts. And the reason I'm also now mentioning these variants and why I explained you the lower bound is that I'd like to mention a few open problems. So first of all, the weak Fauché distance is much less studied than the discrete and continuous Fauché distance. So I think there are many of the results that you have for the continuous and or discrete Fauché distance you could probably also get for the weak Fauché distance. But I mean the paths have different properties, so it's not so obvious, but that I think generally is a nice area to study. You have to be a bit careful because there are some results about weak Fauché distance, for instance. I think looking at approximation algorithm for CPAC curves, that is already was handled in a paper by Harpellet and Reichel, although it's not so obvious. You don't see it immediately, but that case is handled there. Also for the weak Fauché distance, we recently showed that in 1D you can actually compute the weak Fauché distance faster than in quadratic time, and there are also lower bounds for all other cases. But overall, there are many interesting questions, I think, here. So, for instance, general approximation is something you could look at for the weak Fauché distance. Then lower bound for CPAC curves. So the reduction works in 5 dimensions, and it might be interesting to try to bring this down by, I mean, the natural setting are 2 or 3 dimensions, but I think in 4 dimensions there might be reasonable hope, but you have to first understand the geometry of the problem there. Generally, a big open problem, I think, is improving the approximation factors further, because there's still a huge gap to the lower bounds that we have. But this is, I think, a very difficult problem, at least if you want to make a, I mean, I think it's a very difficult problem. But I mention it here because it's an open problem. And with that, I would like to finish. Thank you.
We might have time for 1 or 2 questions. Go ahead.
Okay, so my question is about weak Fauché distance, because, well, I'm new with this topic. My question is, do you have any assumption for how much can we come back in a curve? Because if there's no restriction, why you separate between the names? I guess the weak Fauché distance should equal exactly to the Hausdorff distance. So I guess there should be some kind of assumption that how much we are allowed to come back in a curve.
So it's actually not quite the same. And a possible way to see that, let me just try to draw a corresponding free space diagram. So think of a setting where okay, this is now more kind of in terms of the decision problem. Okay. So here we have lots of free space, and for any point on this curve, I can find a point. I can actually find many points here which are close enough, but I will not be able to find a path even if it's non-monotone. I mean, now for the weak Fauché distance, I am allowed to go down and back, but there will still be this barrier which I cannot cross.
Okay.
Yes. So it's not the same as the Hausdorff. Let me just draw this once. So in the setting of the K Fauché, so that tries to get even closer to be between weak and Fauché distance and Hausdorff distance. There, essentially, what you'll try to get is that you break this up into parts, into K parts, and then have a weak path in each of the parts, which do not necessarily need to line up. So that kind of moves even closer to Hausdorff, but still is different from Hausdorff. Yeah.
Any of the properties of the original space in the free space, like between the man and the dog, and the leash can go through that too. Or maybe the duration of the movement is the passive one.
Yes, so various such versions have been considered. So, for instance, this concept with trees, that is so-called homotopic Fisher distance. So that has been studied. Directions also. So various. I mean, some of these questions. I mean, if you just want to incorporate a specific parameter, it's often, let's say, easy if you just kind of. I mean, if there's a parameter on a cell which you can simply decide whether it's true or not, then you kind of black out that cell or not. But these questions that you are asking, so those are interesting versions, and at least the ones that you just mentioned have been considered. But those, generally there are many variants and many interesting variants also. Yes.
And the last question.
Okay. So regarding your example for these orthogonal vectors rising from this orthogonal vector, I was wondering how generic those examples are, in the sense that somehow are such examples the only source for producing these high complexities in terms of what you said, or is that imaginable that if one somehow ignores such kind of exotic examples, then for the rest of the curve you have a chance at least for somehow improving this the complexity to let them be in equality. Is there any chance for such?
I mean, you could say to some extent this concept of C-packed avoids at least these worst examples, and there's some such versions like they're called. I mean, you have C-bounded, C-packed, which kind of avoid some of this, and then then you can only get weaker lower bounds. Another part of your question, I'd say, could be to say, are there reductions that come from a completely different problem, so not coming from the strong exponential time hypothesis? And there, so far, it's only known how to do it from strong exponential time hypothesis or an orthogonal vector problem. So for a long time, we were looking at threesome hardness because, I think with threesome is simply threesome hardness is a kind of hardness variant that for a long time has been studied in geometric algorithms, but that didn't seem to be the right approach. So I think it's not. So that might be a dead end, but maybe they are different. I mean, so there's whales of problems which are currently used for saying, assume this problem cannot be solved faster than this, then. And maybe there are more problems that would be suitable. But I, so far for the Fisher distance, only saw this strong exponential time hypothesis of orthogonal vectors.
Thank you.
Okay, thank you.
So in your package, you should have a coupon for lunch. Yeah, and where it's served. Go building part of this building. That's